Swayam Prabha. Digital India. Educated India.
So, in this model we will discuss the moments and the inequalities. So, we plan to give 3 lectures in this model. So, the first lecture we will discuss the first 2 moments, mean and variance, and then the second lecture we discuss the higher order moments and moment inequalities, and in the third lecture we will discuss 3 important generating functions, that is a probability generating function, moment generating function and characteristic function. Moments and inequalities, it is a very important topic in the probability or in particular a random variable, because most of the time finding the distribution of the random variable is a tedious task, or it is very difficult to find out the distribution of the random variable, but it is easy to compute or easy to find the value of the mean or expectation, that is basically the first order moment. Similarly, finding the variance, that is of the second order moment, that is also easy comparing to the finding the distribution of the random variable. Therefore, in the probability theory course we discuss the distribution first, then we discuss the moments, then later at the end of the course how much the moments are going to play an important role when we are going to use central limit theorem for approximating some of the random variable into normal distribution with some conditions. So, in that place the moments are playing an important role, and also the moments is the easy measures, it is easy to compute in the real world problems, not the distribution. Once you know the distribution, if the moments exist, we are going to tell the existence of the moments. If the moments exist, you can always find it. If you know the moments of many order, then you can able to identify what could be the distribution of that random variable. That means for a random variable, if the moments exist, we can able to find. Through the moments of some unknown random variable, it is possible to fit the correct distribution for that moments matches. So, in that way I am going to introduce this model, that is moments and inequalities. In these lectures we start teaching first mean and variance. Mean is the first order moment and the variance is the second order moment. Then we discuss the higher order moments, and also we discuss the moment inequalities, and the third we discuss generating functions. So, in this model we are going to have 3 lectures, first on mean and variance, second higher order moments and moment inequalities, third generating functions. Now, we will move into the first topic that is called mean and variance. This is a very important measures. So, let me start with the definition of mean. There is another name for mean, that is called expectation. In many times we use find the value of average of some n values. That is also going to be sort of mean and expectation with some conditions of that random variable. So, that we are going to discuss little later. So, as it is, now I am going to write mean or expectation. Let x be a random variable, RV means a random variable defined on the probability space omega E of capital P. If x is a discrete type random variable with values x1, x2 and so on, it is said that x has an expected value if the summation in absolute of x i's over the i's and the probability of x takes the value xi, if this summation is finite quantity. In such a way, the expected value that is denoted by E of x, the expected value of the random variable x denoted by E of x is defined as E of x, that is same as the summation over xi probability of x equal to xi, summation over I. What we are saying is whenever you have a random variable defined on the probability space omega E of p, if it is a discrete type random variable whose values are xi's, x1, x2 and so on, it is said that x has the expected value if the summation over absolute of xi's multiplied by probability of x equal to xi has a finite value. Why the absolute is there is a possibility the xi's could be positive or negative. So, in the absolute sense if it is going to be finite, without the absolute that is going to be the expected value of the random variable, provided in absolute sense that summation is a finite quantity. In other words, this is nothing but the series. You can think of summation of xi p of x equal to xi as the ai's, whatever you have studied in the calculus course. This series converges in absolute sense. Then without absolute sense the similar series you made it summation of xi with the probability of p is equal to xi, that is going to be the expected value. If the series is convergence in absolute sense, then it is going to be converges here. So, we are using the calculus sequence convergence concept to conclude expected value of a discrete random variable exists. So, now I am going for if the random variable x is a continuous type. If x is a continuous type random variable with the probability density function is f of x. It is said that x has the expected value if the integration minus infinity to infinity absolute of x f of x dx is finite quantity. In this case, the expected value of the random variable x denoted by e of x is same as integration minus infinity to infinity x times f of x dx. Note that integration minus infinity to infinity f of x dx is 1, because f of x is a probability density function, whereas here if the integration absolute x f of x dx is a finite quantity, then you can say that the expected value of the random variable x exists, and that value is same as e of x. It is a notation that is same as minus infinity to infinity x times f of x dx. So, the provided condition is very important. If the provided condition is not satisfied, even you get the value of this integration without absolute, that is not going to be called it as a expected value. It is very important to conclude in the absolute sense the summation for a discrete type random variable, integration in absolute sense for the continuous type random variable. If it is a finite quantity without absolute sense, that is going to be the expected value of the random variable. I am going to give one example for a random variable in which the expectation does not exist, and one or two examples for expectation exist. Example 1, let x be a continuous type random variable with probability density function f of x that takes a value 1 divided by pi times 1 plus x square, where x lies between minus infinity to plus infinity. The probability density function is 1 divided by pi 1 plus x square, where x lies between minus infinity to plus infinity. You can verify whether this is a correct probability density function by integrating f of x from minus infinity to plus infinity. You will get the value 1. This is greater than or equal to 0, therefore it is a probability density function of continuous type random variable. Now, you can compute the integration from minus infinity to infinity absolute of x f of x dx. If you compute this quantity, that is same as 2 divided by pi, it is a even function. So, 2 divided by pi 0 to infinity x divided by 1 plus x square dx. If you do the simple calculation, you will come to the conclusion this quantity is going to be infinity. You can make it as a homework computing this integration, that is going to be infinity. So, since this quantity is going to be infinity, you can conclude the expectation of x does not exist for this random variable. Even though you will get the value from minus infinity to infinity x times f of x dx for this problem, but since in absolute sense this integration value is infinite, therefore, the mean does not exist. I will take a next example where expectation exists. Let x be a continuous type random variable with probability density function, that is f of x, is 2 times e power minus 2x when x is lies between 0 to infinity, otherwise it is 0. You can verify this is a probability density function or not. If you integrate, you will get the value 1 and between the interval 0 to infinity, because from minus infinity to 0 it is 0 and it is a positive function, therefore it is going to be a probability density function. Since the possible values of x is from 0 to infinity, you do not need to check whether this is going to be a finite quantity in absolute sense. You can directly compute if that is going to be a finite quantity, then that is same as the expectation. Let us compute minus infinity to infinity absolute of x f of x dx, that is same as, since f of x is going to be 0 between minus infinity to infinity, therefore this is same as 0 to infinity of x times f of x is 2 times e power minus 2x dx, that is same as, if you do the simple calculation, you will come to the answer, that is 1 divided by 2. So, since this is going to be a finite quantity, therefore we can conclude expectation x, that is going to be 1 by 2, because the f of x is going to be greater than 0 between the 0 to infinity. Therefore, in the absolute sense answer is finite, that is same as without absolute also. Therefore, the expectation of x is same as 0 to infinity of x times f of x dx, that is going to be 1 by 2. So, in this case the expectation exists for this continuous type random variable. Later we are going to say this random variable is exponential distributed with the parameter 2, that we are going to discuss later. Therefore, the expectation of exponential distribution random variable is reciprocal of the parameter. So, here the parameter is 2, that is 1 divided by 2, it is an expectation for the random variable. We can go for one more example. Let x be a discrete type random variable with probability mass function is given by p of x, that is 1 divided by n when x takes a value x1, x2 and xn, that is going to be 0 otherwise. So, this is a probability mass function of a discrete type random variable with the possible values are x1, x2 and so on xn, and this could be positive values or negative values, or it could be 0 also. Okay. Now, we will find out whether expectation exists for this one. So, if you compute in absolute sense of xi's, probability of x equal to xi and summation over I. So, here it is a summation is I is equal to 1 to n. This is same as absolute of xi's, probability of x equal to xi is 1 by n, I is equal to 1 to n. This is nothing but 1 divided by n summation of xi's. Since we have taken all the possible values are from minus infinity to infinity, the summation of xi's, that is also going to be finite quantity. Therefore, the expectation of x is going to be 1 divided by n summation of xi's. This is going to be the expected value of the random variable x when x is a discrete type random variable with the probability mass function 1 by n for xi's or n values. But you know that 1 divided by n summation of xi's, that is nothing but average. So, whenever the random variable has a equiprobable at a finite number of points, in that case the mean or expectation, that is same as average. Later we are going to conclude this random variable is called a discrete type uniform distribution. That means for a discrete type uniform distribution, the mean expectation, that is same as average. That is what many times when you have a n values, you make an average out of it. So, the average is same as considering that as a random variable whose probability is same as 1 divided by the total number of information or total number of values. In that case, a mean and or expectation, that is same as the average. Now, we will discuss a few important results for the mean as a remarks. The first remark, the expectation of a constant is a constant. If you find the expectation or a mean for a constant, that is going to be a constant. This result can be proved easily. You can treat a constant as a random variable whose probability is 1, taking only that value. Therefore, expectation of a constant is nothing but a constant times the probability of x takes the value constant, that is 1. So, 1 into alpha, therefore it is alpha. It can be proved easily. As a second remark, suppose you have some constant times random variable plus another constant, here a and b are constants. In that case, just now we made it expectation of a constant is a constant, but here it is a linear combination and the constant can be taken out with the expectation of x plus expectation of a constant, that is same as constant. That means expectation of a constant times random variable plus another constant is same as constant can be taken out. Third remark, if probability of x greater than or equal to 0, that is 1, the unit mass is distributed between the interval 0 to infinity. In that case, if expectation exists, the above two results also, above the second result also, if the expectation exists, then this is true. So, if E of x exists, then the expectation of x also going to be greater than or equal to 0. This intuitively also you can say, if the probability of x is greater than or equal to 0 is 1 and if expectation x exists, then the expected expectation or mean value of that random variable is also going to be greater than or equal to 0. This also can be proved in from the definition the same way, since whether you are going to use x is a discrete type or continuous type or mixed type, you can use the same definition for the existence in the absolute sense, then you can conclude if it is exists, then that value is going to be greater than or equal to 0. When I give the definition, I have given the definition for the expectation for a discrete type and the continuous type. I have not given the definition for mixed type, but the mixed type is the combination of discrete and continuous. Therefore, wherever there is a mass, you can do the summation. Wherever there is a density, you can do the integration. Therefore, the expectation formula is a combination of both discrete and continuous. Therefore, I have not given the definition. Okay. The fourth remark, remark number 4, let x be a random variable and y is equal to g of x is a random variable. This we discussed in the last module. X is a random variable, g is a Borel measurable function. In particular, you can think of a continuous or piecewise continuous function. Therefore, y is also going to be a random variable. Then you can find the expectation of g of x, that is same as summation of g of small x and the probability of x takes the value x summation over x if the random variable x is a discrete type. If x is a continuous type random variable, minus infinity to infinity integration g of x f of x dx when x is a continuous type random variable. This can be proved provided the expectation exists. Provided the expectation exists, you can find the expectation value of a g of x with the summation if it is a discrete type, with the integration if it is a continuous type. Why this result is very important is you are not finding the distribution of g of x, but with the help of the distribution of x, you are finding the expectation of g of x provided it exists. Therefore, this is a very important result in the sense you do not need to find the distribution of g of x, whatever be the distribution of g of x, as long as if it exists, you can find the value of expectation of g of x with the help of the distribution of x, means if it is a discrete type random variable, if you know the probability mass function, if it is a continuous type random variable, the probability density function of x. You can find the expectation by the summation or the integration without knowing the distribution of g of x. So, therefore, we will be using this property again and again whenever you want to find out the expectation of a function of random variable. Not only this definition, similarly later we are going to introduce many random variables or random vector of size n with the n random variables. There also you can go for expectation of functions of random variables in the similar way. Therefore, this is a very important result, one can find it.